This is the last lecture of my course, and I hope you've enjoyed learning something at least. Maybe not everything was understandable or not everything was within your grasp. Some things may have been too simple, but I hope that you've got a flavor for the whole topic of materials that are used in electronics. We've been looking at the last topic in electronic polymers, polymers that are used in electronics, organic materials in general, though I keep saying polymers, but there's non-polymeric organics that are used too. And so today what I'll do is I'll try to wrap up very quickly some of the key concepts in the conduction process and doping in polymers, why they behave as conductors, and then we will look at some applications. That's really what I want to focus on, because that's where the excitement is, the possibilities that are there with organics. Yesterday what we saw was that it's possible, looking at acetylene, polyacetylene for example, a very quick glance through yesterday, that you have it in two forms, the cis and the trans isomers, and undoped, this has got a very low conductivity, something like 10 to the power minus 13 conductivity. This is more like 10 to the power minus 7. And then we saw that if you dope it, you can go up to about 10 to the power 4, 10 to the power 5 Siemens centimeter per centimeter. So this is the big changes that we can bring about by doping. Before we got to that, we wanted to look at the, I mentioned the word Solidon, and we were going through that when we stopped the lecture. Basically, the idea was that the material can exist in two forms. The trans form itself can have two types of structures. Basically, it's the same structure, but we can either have it, this is the trans polyacetylene. I did this yesterday, so I'm not going to go in great detail, but it could be either something like this, or the other form could be something like this. Am I getting this right?
So the two double bonds cannot.
I knew I'm making a mistake somewhere there. Very good, thank you. It's the same structure. I mean, it could be either this or this. Both are trans. Yeah, I mean, there's no difference except you see the direction of which way is the double bond. That's all is the difference there. Okay, otherwise, structurally it is different from cis. That's why it's a different isomer. But it's either this or this. Both are exactly the same in energy kind of values. So these were the two different forms that we could think of. And then we were looking at the question, what happens when both of these join together? And we end up with two single bonds coming together at some place. So this and this coming together, we end up with two single bonds over here.
Sir, what that rounded portion, is there any carbon atom?
Which one are you talking about? Over here? Here? These? Oh, this area?
Yeah.
Oh, yes. And that's part of the problem, because I'm not putting in all the carbon atoms. All right, you can put it in. And that's the problem. Here we have a carbon atom with two bonds. Okay, and we know its valency is 4. Then in such a situation, what is formed is called a soliton. That black dot there represents what is known as a soliton. All right? And we may have an anti-soliton, which is the mirror image of a soliton. Yes?
Sir, there are two chains. We are using two chains. The end part of the chain will always have a single bond.
We are using terminators, remember that. The initiators.
Yes, sir, the initiators. That's why the carbon will have a single bond there. I mean, if carbon is being attached to an initiator, then it will have single valence. Let us suppose with Cl or H.
Right.
So if we are using two end points that had been attached to an initiator, so we are having two single bonds. And if we are attaching them, then how could we have a carbon again within them? I mean, right here, if we consider that the carbon in between the circle is associated with this chain or this chain.
It doesn't matter which chain it is associated with.
But sir, that bond...
I mean, they are not existing as separate things hanging around like this. This is forming during the process of polymerization. You remember, what you had was C2H4.
Yes, sir. C2H4 hold to N.
And then when the bonds break up, during the process of polymerization, at some places, these two types may come together.
Sir, that carbon in between the circle
Yes.
must be in maybe from this one or
Yes,
from
yes,
this one. So let us suppose if it is from this left hand side,
Right.
then right hand side carbon has when it came to be attached, then it was of this sort, carbon double bond, and this way only just one single bond.
Right, and there is a hydrogen also. I'm not putting in all the hydrogens. Right? I mean, I understand your question. See, the thing is, when it comes here, you've got the hydrogen still to worry about here. So that satisfies 4, that satisfies 4.
No,
No,
not
sir,
that
we are asking that when you are joining two molecules,
Okay.
there are initiators, so that means at the end of the chain there are 2 carbon atoms for both the molecules.
Yes.
So if you join them, so there is only one in the picture shown.
Sir, I mean to say that
There should be another carbon, is what you're saying?
yes, sir, one more carbon should be there.
Why?
Because sir, because the initiator will always the end to which the initiator has to be attached will always have a carbon with single bond there. And
No,
in
it
this-
depends on what is the initiator. I just gave you a couple of examples. We could have other initiators too.
Can you have double bond?
Yeah,
initiator?
maybe. I'm not certain of these things, but the point is, I just gave you a couple of examples. We don't have to limit ourselves to those. Those were the obvious ones that were there. So don't get confused. I mean, it is possible to create a structure like this. This exists. All right. Don't think that we are limited to those either single bonded OH or Cl type of initiator, and so nothing else is possible. Only one side is there. Like there are other fragments that are forming. This process is taking place during the polymerization. Okay, not everything is completed. The reaction is still polymerized. It's like a reaction. Either it's addition or condensation we saw. And during that process, some fragments may come together. The whole thing hasn't even completed. Maybe the initiator molecule hasn't terminated the thing on the other side. Whichever way it is possible to create such a structure. Okay. I'm not going to get bogged down here. I told you frankly, I don't understand the whole details of it. So I don't want to get bogged down because I think I want to complete the applications which are interesting. I just want to give you a flavor for this topic and sort of create an appetite in you for polymer electronics. If I succeed in that, I think that would be the goal. After that, you go and read, get into the textbooks. Now there's a lot of material that is there. Okay. Whatever way it is, it's possible to create a soliton like this when these 2 single bonds come into existence, and you can also create anti-solitons. Now, let me give a sort of a definition of a soliton that I will just write out for us. It's a structural, okay, it's a structural distortion. Even these are not things that I understand very well. In a conjugated polymer. That's why I prefer just giving you the definition as I have it from a text. And is generated when a single bond meets another single bond. So we have the keywords there. It's a conjugated polymer, alternating double and single bonds. But here we have a place where a single bond meets another single bond. At that point of distortion, where the soliton is formed, we have localized non-bonding electron states. Effectively, what that is like is similar to an N-type impurity in silicon. I'm going to use familiar terminology to give us some handles on understanding this. So basically, what it's doing is to introduce some state in the energy gap, which is behaving more or less as if it's an N-type impurity in silicon. Okay? So I'll just leave you with that definition. Very shortly, when you in these kind of materials, when we excite from valence band to to conduction band, in very short time, 10 to the power minus 12 seconds, that will decay into a more stable state, which consists of the soliton-anti-soliton pair. That is what is happening to create the method of conduction. And yesterday I told you that a soliton you can think of also, in addition to this idea of N-type impurity, a soliton wave can be created by the flipping of double single bonds. You had this situation. And if a double bond flips this way, okay, this was our situation. And just imagine that one of these double bonds flips here. You end up with the soliton having moved from here to here. And if the process repeats itself, then we have as if something similar to a traveling electron wave. I will not go into the band structure and things like that, but the idea has been, people have calculated band structures and so on, and have shown that when bond lengths are roughly equal, then you have more conducting properties, more metallic behavior. Metallic behavior. And with increasing inequality in bond lengths, we generate gaps and so on, and it becomes more and more like a semiconductor. It turns out that in the region around the soliton, bond lengths are roughly equal. So the point here is that from simulations and things like that, we know that if the bond lengths are roughly equal, it's got a more metallic type state, conducting state. And so if you have enough of solitons, you may think of it as there is a region that is going to be more or less metallic around the soliton, and these start overlapping. You have lots of solitons. If the density of the solitons is high enough, this sort of a region that is more or less metallic in its behavior starts overlapping. And so you create a conducting path in the polymer. That is one idea that is used to explain the conduction over here. I'll now quickly go through doping. We need to be able to dope the polymer, both N-type and P-type, in the same way as we want to do for the semiconductors. But when we use the word doping here, it is a little bit different. We are not putting in ppm level or ppb level of things. They are in much larger quantities. So the dopants that are used are very different than traditional semiconductor dopants. Nevertheless, they function in similar ways, and that's why the terminology doping is used. If we consider with our argument again polyacetylene as before, we can have a neutral insulative structure which we saw earlier, simply the single double kind of stuff. There's only carbon there and hydrogen. And the point is that this could be either, I'm looking at the transform here, but it could be cis also. But once we dope, there's no more cis-doped polyacetylene, it's always trans. So the process of doping apparently transforms the polyacetylene to the trans form. So as long as it's undoped, you can talk of the cis and the trans with the different conductivities. Once you've doped it, you end up with the trans-doped isomer. That's all we have. Now we can take this neutral form and oxidize it with anions, and it is equivalent to a p-type doping. Basically the same structure here. Sorry, that's a single bond there. And so on. We remove an electron, that's the process of oxidation, and we do this with something like a ClO4 ion, perchlorate. And the structure that is formed then will look something like this. A positive charge there. And then we have the chlorate ion attached here, perchlorate ion attached here. I'm sorry, this has to be a negative sign. ClO4 minus, it's an anion there. Okay, that is attached here. And so on. This is the equivalent of p-type doping in polymers. We can also have n-type doping. Basically, it's a reduction process where we reduce it with cations. And again, as before, we have the same undoped structure. This time we add the electron and some kind of alkali types. So in this case, it is doped with sodium. we end up with, sorry. Did I get that right?
So that's the double bond and minus.
No, we are going to have a minus here.
Yeah, and double bond also.
On this side is a double bond, yeah. And then we'll have a sodium that is attached to this carbon here. Okay? So this is the equivalent of what is the N-type doping. So just like in semiconductors, we need to create P-type doping, N-type doping. Now you can think of PN junctions and so on. All right? Once we have doped it now, remember our conductivity has gone much higher than the undoped form. There are different methods of doping that are used. You can use some chemical oxidant. And examples are iodine, nitronium species, transition metal salts, okay. So you can use oxidants like that. You can also use reducing agents like the one we saw earlier, perchlorate. I'm sorry, sodium related. So sodium, one example is naphthalide. Or you can, these are chemicals that you can use. Or you can actually use electrochemical techniques too. And you would introduce then the ion, the perchlorate ion, or boron tetrafluoride, and so on. So it's much more complex than a simple introduction of arsenic or boron or something like how we did there in plain old semiconductors. But the effects are the same, ultimately. And note that a number of these dopant things are also pretty toxic. There's another one that's used, I think, arsenic pentafluoride, ASF5 or something like that, okay? So they're not easy to handle. Of course, arsenic in its arsine also in semiconductors is not easy. But a lot of these are toxic things that we have to worry about. And what this doping does is that it affects conductivity, which we expect. But in addition, it also affects the stability of the semiconductor. So we have to worry about, okay, I increased its conductivity, but have I gone and made it more unstable? So the choice of the dopant and the way we dope it and all may, or how much we can dope, could also be a factor that is influenced by the issue of stability. It affects the morphology, what kind of structure it has. And then there are other properties, basic polymer properties that get affected. So it's not a simple thing, I just put in some dopant to whatever. I'll come to that. The biggest problem with these organics is its instability. That means in exposure to, say, for example, air, moisture, ultraviolet light, ozone, they begin to degrade. And it is related to, at least as best as I understand, bond breaking and so on. Say, for example, UV light, there's enough energy to break some of the bonds. That means the polymer begins to change its structure. Okay? Remember, in our semiconductors, one of the good things for things like silicon and all that, it's pretty stable. You leave it out. Just because light fell on it, you change conduction, but you won't change the basic silicon's properties. Silicon still remains silicon. It's very strongly covalently bonded. But in the case of the polymers, exposure, it's got so many groups in it that some of it may start absorbing moisture and things like that, which is not a major problem with inorganic semiconductors, though some of them are affected. But here we have that as a major issue. And that is one of the challenges in polymers, the stability issue. So these are the different things that doping also influences. This one? The methods of doping. It can be chemical oxidation, chemical reduction, or electrochemical methods. All right? Very good. So how does the conductivity change then with doping? If we look at a plot of conductivity, in Siemens per centimeter versus doping concentration. Basically, the units are dopant per CH unit. So remember, in here we've got the CH. So how many dopant atoms are there per CH unit? So if we start, we end up with something like this. Slowly it increases, and then there's a very rapid change. With a slight change in doping, we get significant change in the conductivity, and then it sort of tails off and saturates. Excuse me. The exact mechanisms that are involved in the different polymers in conducting are different. Okay, in different regimes, it may be different. So what is the exact mechanism that causes these changes to occur could be very different in the different regimes within the conductivity. Words like polarons, bipolarons, and so on are used to describe the exact mechanism that is used. I'll just illustrate what is a polaron. A polaron is the result of the interaction between an electron and the lattice, electron and the phonons there. Okay, this is basically what's called a polaron. And then what is happening at these low doping levels? Why does it suddenly change when you're at another level, and so on? Questions are there. I'm not going into the details, but at low doping levels, they say the mechanism is related to what is called polaron hopping. And then maybe at higher doping levels, these things called bipolarons are involved, where you've got two positive charges coupled with the electron. So we have different mechanisms in different regimes of conductivity. Okay, the point is not to go into the details of the mechanism, which I really don't understand, to be very frank, but there are different mechanisms involved. This is similar in some sense to what we see in semiconductors also. Normally we understand the doping behavior. We get an excitation from the dopant level into the band gap and so on. But as we go on increasing the carrier concentration, remember we had a curve. If you go too high in carrier concentration, you begin to have now hopping conduction and things like that, where the donors or acceptors are so close to each other that they sort of tunnel through. And so even in semiconductors, you've got different mechanisms. Normally, we don't deal with such a high level of conduction, so we simply look at the lower levels of doping, and we say, okay, excitation from the donor level or acceptor level into the conduction band or valence band. So there's different mechanisms there also, which we don't go into in much. But the same idea is here, that we have different mechanisms to account for these conductivity changes. I mentioned the word band gap earlier when we were talking of Solidon. And people have calculated what might be the band structure for these kind of polymers, and band gap values have been estimated. It is a difficult thing because our lattice, we don't have sort of like a very ordered crystal lattice. We are talking of disordered materials in general. But nevertheless, people have attempted these. And in the case of neutral polymers, here are some values. Polyacetylene, it's somewhat like silicon, 1.5 EV. Then there's one called polypyrrole, which is the other class we spoke about, the heteroaromatic group, which has got something like 3.2 EV. Polyphenylene, or phenylene, 3.5 EV. Here we are into the UV. This is in the infrared, and this is in the UV. And in between also there's stuff with polythiophene, 2.2 EV, and so on. And some of these can be tailored, putting in different groups into it. You can tailor it. That's the beauty of the polymers. You can adjust it to what you want. So you can imagine, even for optical applications, I can tailor the band gap to get different colors of light, for example, out of these kind of materials. So that's and it's very simple. That was the thing we saw. You asked a question earlier, one of you, about stability. And there's two basic types of stability we're talking about. One is known as the extrinsic stability. And this is the main kind of stability I was talking about that is related to the external environment. How stable is it in the presence of oxygen, moisture, say some peroxides, and so on. This stability depends on what kind of groups and things like that are there in the polymer attached to it. That will determine how reactive it is either to oxygen or to moisture and so on. And most of the polymers have a problem with this. And so what we usually do is we use some kind of a coating to encapsulate it. In other words, we just prevent the oxygen and the moisture and so on from getting to the polymer by coating it with something that acts as a barrier layer. And then there are some intrinsic stability issues. That there are some polymers that even if you keep them in a dry, oxygen-free environment, they will also degrade with time. You don't even need oxygen or moisture, but just in themselves, they will start degrading with time. And the origins are thermodynamic. In other words, there is a structure that we have created which may be, let us say, metastable. And after some time, with time, it is changing to a more stable form. Thermodynamics is slowly driving it in that direction. It has nothing to do with whether there is oxygen or moisture. It's just changing its state. And this is some kind of chemical reaction that may be going on irreversibly within the polymer that accounts for it. Some kind of irreversible reactions. Another reason could be some thermally driven processes. Even at room temperature, there may be enough thermal energy to cause some processes to be activated and gradually degrade the polymer. I'm going to now quickly go through the different applications that I have in mind. And I will focus only on one or two as time permits, but give you a glimpse of what is possible. One of the common applications would be sort of a passive application, which is coatings. You may protect the semiconductor against photocorrosion. Some semiconductors are sensitive to light and degrade. So some polymer coatings can help in that area. Coatings are also used to prevent corrosion in general, but we are not looking at that application. You also have that certain polymer coatings prevent the buildup of static charges. Very important in these days. Before you touch the insides of your computer, they tell you make sure you're grounded. Otherwise, you may damage your chip because you generate static electricity. And all of that gets discharged across your chip, and that's the end of your chip. So you find people who actually know what they're doing, putting on certain bands, hooking it up to a ground, and then only they will touch. Otherwise, you can ruin the insides of your computer because of the static charges that you build up simply walking around the place. You generate charges, and in winter, you know how that is. You've got crackling sounds, you comb your hair. You carry a lot of static, and when that is discharged across a chip or memory or something, you can lose that whole thing. So static is a very important issue, and it prevents the buildup of static charges. So when used as coatings, these are some of the ways in which it is used even in the electronics field. The second application is in the area of sensors. There's all kinds of chemical sensors that are being created, I would say chemical and biological sensors, which are using polymers functionalized in different ways, making them more sensitive to a particular environment, to a particular gas, to a particular chemical, for detection in trace quantities. You can think of applications like DNA detection, drug detection, and separation. You've got a gas leak somewhere, you want to detect it in trace quantities. The polymer can be made sensitive by tailoring its molecules to be sensitive to a particular gas or a chemical. And so it finds tremendous applications in the field of sensors. A common example is polypyroles. The conductivity changes when it is exposed to, say, NO2 or ammonia and so on. And if you can calibrate your device, the conductivity of the polypyrrole versus the concentration, it's very easy to then actually quantify and say how much of this is there. So this is one of the kind of applications. You can make more sophisticated devices that are called ChemFETs. We know what's a FET. You can make an ion-sensitive electrode as part of the FET. So it is sensitive to a particular species. And when that species comes and sits on this electrode, the properties of the FET are affected. And so we can measure it by actually putting the FET into a solution or things like that. Very challenging, because now our whole electronics must be able to sit inside some environment where these species, it may be a liquid. The other day I was seeing a picture, I forget where it was, where it said, this is the only chip, it was sort of advertising for something, which is designed to be touched. And you see the picture of a man or a woman, I don't know, somebody's hand, just a finger pressing down on a chip. And you know, that's the last thing you want on normal chips. But that particular chip is designed for fingerprint identification. So the top part of it is designed to actually take your fingerprint. It's sensitive to that. And then the stuff in there will do all the analysis and spit it out, whether you are allowed to enter something or not, or who are you, and so on. People are coming up with incredible applications related to these sensors and detectors. These are sort of chemical ones. In the area of biological sensors, we've got something that could be used as a glucose sensor. In combination with an enzyme called glucose oxidase, it is able to detect the presence of glucose. Okay? The same pyrroles that are there, polypyrroles. So you can imagine for a diabetes patient, you want to know what is the sugar level. You don't have to go to the doctor. We can make a tiny little sensor, little device, that at home the patient just, puts a drop of blood there, pokes, and right there you get the result. It's internally calibrated, and it will give you a result on the spot in a very, very short period of time. Very exciting things are possible with this. The third one, polymeric ferroelectric RAM. I'm going to come back to this if time permits to go into a little bit more detail. It's called PFRAM. You know what's a RAM, right? Random access memories. The larger the RAM, the better, the happier we are. Yeah? So we try to put in as much as we can into our system. There are different approaches to RAM, that's the storage and retrieval of information, making it more compact, cheaper, faster, and so on. And RAM, you want it to be faster at least than your hard disk. So the technologies that are used are very different. With hard disk, you can store huge amounts of data, but storage and retrieval times are longer. With RAM, you want to store maybe smaller amounts of information, but you want to be able to store it and retrieve it very quickly. So the technologies that are used are very, very different. You've got all kinds of technologies, DRAM, SRAM, we've got all those acronyms that are there. And then you've got ferroelectric RAM that is called FRAM that is coming out. And then you've got PFRAM, polymer ferroelectric RAM. And these are, some of them are competing technologies. And another area where this is very useful is in what are called flash memories. Your video cameras and things like that now, digital cameras, you want to be able to store information very quickly, capture it, and then it has to somehow be transferred into, say, your hard disk or something like that. So these are all areas where the polymer ferroelectric RAM is also making a very major entrance into it. I'll take this up a little more in a second. Basically, it is, as you see the word ferroelectric, there are two states in which this material can exist in, two conducting states, let's say. And you can flip it between these two, and that's how energy is stored. One is the 0 state, I mean, information is stored. One is the 1 state, and one is the 0 state. And they are stable. So you have to do something to it to flip it. And that's particularly in the case of ferroelectric, because these are very stable, they're non-volatile. So simply because the signal was removed, the voltage that is applied or whatever, the information isn't lost. And then you have volatile memories where you have to go on refreshing it every few microseconds or something like that. Otherwise, the information is gone. So polymer ferroelectric RAMs are useful in non-volatile memories. We'll come back to it, but I'll give you a little more detail of that if time permits. But these allow you, the PF RAMs, high density storage, high speeds, low power consumption, non-volatile, so you don't need to go on refreshing it, which is also related to the low power consumption. Because if it is something that needs to go on being refreshed, even if you're not using that particular memory point, you still need to supply energy to it to go on storing the information in sight. But if it's something that once you've stored it till you need it, it doesn't have to be refreshed. The power that is going to be consumed in storing that information over the long time will be much lower than something which needs to be refreshed. So we'll come back to this, time permitting. The fourth application are conductive adhesives. Basically, some kind of monomer is placed between two conducting surfaces. And then you allow this to polymerize. Okay, so the polymerization is taking place in situ there, between these surfaces. And these are special polymers that allow the passage, they're conducting. And so when it polymerizes, it forms the bond between these two surfaces, and at the same time it allows the passage of current through it. So you can use it not only to make it like an adhesive, glue, very strong, but it also allows the passage of current through it. Then the whole area of, I mentioned very briefly, I think, in the last class, biocompatible polymers. Now here some weird ideas come up. You know, you make your sensors and things like that, that's nice. But if you put it into your body, let's say it's something that sits inside under your skin or something, we are looking at, will the body reject it? So that's one area where they're talking of biocompatibility. But it's even getting more bizarre. They're talking of nerves made of polymers. A brain made of polymers. Conducting, storing information, and so on. I don't know how close to reality all these are, but these are sort of the kinds of things people are doing, they're imagining about. I wouldn't sit and think about these things, at least not yet. But it's very interesting to think of the possibilities that are there. Nerves, somebody's hand got cut off, you want to replace it, you know, attach it back again, and you want something to fuse the nerves back together. Or here we've got a little polymer glue kind of thing. We just stick those nerves back and it starts working again. It would be fabulous if we could do that. It's part of it. You had an accident, part of your brain got damaged. No problem. We've taken a scan ahead of time. We've stored all that part of your brain, what type of information was there. We put in a polymer brain in there and attach it, and there it works. I don't know if it'll ever be reality, but it's fun to think of the possibilities, right? Here's another major area, displays. And again, I'll try to come back to this if I can. It's a tremendous impact it's going to make. The display technology is going to change. As I told you, they've already got displays that will simply be folded and put into your pocket. I saw a picture of one that could be folded to, I think, a diameter of something like 1 centimeter. I mean, it's so flexible. You don't have to worry about it breaking, or just fold it up. Don't put a crease on it, but just fold it up and take it where you want. It's lightweight and low power consumption. Look at the bulky stuff we have that for television monitors, computer monitors today. All of that, you just simply hang it up on the wall, and that's your computer monitor. Or whichever way you want. Lay it out in front of you if you like it that way. Tremendous impact will be made in flat panel technology. But there are some problems that are related to lifetime and switching times. You must realize that for a display technology, particularly for one that involves moving images, you've got static displays that simply show an image and then don't have to worry about it for a while till it changes, say advertising. You have a hoarding that is made of a big flat panel display, not painted, but it's all electronic. And then every minute or 2 minutes it changes to a different ad electronically. But if you're talking of a display that should be used for a television screen or for a computer monitor, the information at any particular pixel has to change very rapidly, because that's how you'll get your moving images. And in that case, switching times, how rapidly you can switch it on, off, and so on, become very critical. But for static displays, this is a great thing. So you can make huge ones, meters maybe. And for static displays, it's already it's in use already. But for dynamic displays, it's a problem. I'll see if I can come back to that in a second. Or the LED technology, light emitting optics that can be produced with polymers. The seventh application, I don't know if I'll have time for all this, but at least let me give it to you what are possibilities. Battery technology has been radically changed. Now we are talking of lightweight, rechargeable batteries that are based around some kind of polymer. It's already there in the market. We've got polypyrrole lithium or polyaniline lithium. Excuse me. Okay? They are the integral part of the device, of the battery, not simply the casing. We can always think of the casing as being plastics, but no, it's part of the device, the polypyrrole and the polyaniline. One very recent one I was reading about is polymer lasers. And there are various groups working on it. And one of them has produced a laser out of this kind of class of materials called polyfluorines. You can tune the output in the visible region from 400 to 700 nanometers anywhere. Depending on the structure, you can make it produce light in different places. Very simple to process. And then you can imagine the flexibly shaped lasers. Now, wouldn't you like that? Now we are, a rigid rod structure or a tube or something. Here we got, it could be a flexible shape, some arbitrary shape it could have. Complex, which we can shape it. We are not so restricted as in the case of other kinds of lasers. They are talking of paint on, in the connection with lasers, LEDs. You don't need a tube light like this in the room. You just paint the whole surface with a organic LED. And you come and you turn it on, the whole surface glows, giving you light. You don't like the whiteness in it, you want it to be slightly redder, you can adjust that. And so the environment around you can be tailored depending on your mood. You want brighter rooms, you want darker rooms, all kinds of interesting possibilities that are based around the LED optics technology. Here's another one that is coming on, transistors. They've actually demonstrated transistors made out of polymeric electronic materials. I have about 10 minutes, and what I'd like to do is, if possible, to touch a little bit in detail on two things, maybe one. One is the display technology and one is the PF-RAM. So these are overall just an overview of your kind of applications. There are more. But let's go back to display technology, or another related areas, OLEDs, organic LEDs, PLED, polymer LED. These are some of the names that are given to it. The competing technologies in display technology for monitors and things like that, you think of it. What is it? We have the cathode ray tube, CRT, bulky, heavy, consumes a lot of power. But that's the primary existing technology. And then when you come to laptops and things like that, you got LCDs. What are LCDs? Liquid crystal displays. We didn't even have time to talk about liquid crystals in this course, did we? That's a whole different category, beautiful category of materials used for electronics. I think no time was there, but that's the existing kind of technology for laptops and things like that. Low power. But what's the problem? One of the primary problems with LCD is the viewing angle. Have you ever tried to look at a laptop screen when you're standing somewhere here and the screen is in front of you? So you can't see anything. If you're within a particular angle, is the screen visible to you even? Otherwise you see nothing. Whereas other technology like CRT and all, it's got a much wider viewing angle. You could be practically anywhere in front of it and you can see it. That's one of the primary drawbacks to LCD technology. And then you also have LED technologies that are based on semiconductors. And here we are talking of a class of materials, say, based on gallium nitride, where we are talking of white LEDs. Okay? Or you may have a combination of a red LED, a green LED, and a blue LED, and so on. And then you have the organics. And by comparison, we will see that when we compare LED technology, of course, it's got a much wider viewing angle and so on compared with LCD, much cheaper than some of the other technologies that are there, and much lower cost in terms of power consumption and so on. This is very expensive technology compared with this. Okay? So these are the competing technologies. There may be a few others now. Plasma displays are also there. That's another area, and so on. But this can make a big impact because it's light, cheap, and so on. So here I'll quickly list some of the things that are related to it. It's low cost. That's one of the advantages of these organic LEDs. You can use flexible substrates, and so we can, as I said, simply roll it up. It's light. It's got high brightness. No directionality limitation. By that I mean that it's unlike an LCD in that we can view it over much larger viewing angles. Relatively high efficiencies. They're still working on this efficiency part of it to make it more efficient. But it's much more efficient than a bulb in terms of converting electrical energy to light energy. Much more efficient. But they're trying to get it up till it's another 2-3 times more efficient. You can get multicolor. If you like, you can tune the color, different shades. It's you can use things like inkjet printing. Can you imagine that? This is commercial technology I'm talking about. You want a circuit with an organic LED on it. You produce the circuit on your screen. You put in the organic template into your printer, not the real printer in your office or home, and then you say print, and the circuit is printed out. Because they use conducting, it's fundamentally the same kind of inkjet technology that you're using in your inkjet printers, except that instead of real inks, they're using conductive paste and so on, and organic things that are in solvents. And you print it out, dry it, and there you have your device. Fascinating. You can use rolls, not little chips and things like that. You have these huge printers, maybe this wide, and the feed is not single sheet paper, it's rolls of paper, rolls of this polymer. And there it's just fed through and printed, and you cut it out and you've got LEDs. The other process that is used is spin-on coating, equally cheap, fascinating. A drop of the polymer onto the substrate, spin it at high speed, centrifugal forces, spread it out thin, put a top contact, a bottom contact by evaporation, there you have your device. So it's so easy to process, that's what makes it so interesting in its use. But life is not that simple because we have problems too. If everything was just easy, that wouldn't make up for any challenges. Here are some of the problems. The drawbacks include electrical contacts are still an issue. They're working on that. Okay, see, these are some of the negatives. We saw the stability is an issue, so environmental stability. Lifetime. Low mobility. So if you're talking of high-speed devices, there's no way as yet we can use this. So, or you're talking of higher frequency of application, you can't use it. And then issues in purifying the polymer. Silicon and all have come to the point of being some of the purest materials available in the world. It's very difficult to beat all that. But polymers, not yet there in that regard. Doping, there are still some issues that they're working on. I'm supposed to close. Oh boy, I had so many more things to say here. I don't know if I can cover anything more, other than maybe to give you a quick glimpse of how you can have the structure of a polymer, perhaps. I mean, one of these LEDs. I'll just draw a quick thing and leave it there, okay? Shut me down soon. You've got silver paste kind of tip over there. This is a magnesium silver alloy contact. This is called the electron transporting layer, ETL. In this particular case, it is also combined. Some cases you may have a separate layer called the luminescent layer, but it is both the electron transport layer and the luminescent layer. Below it you got what's called a hole transport layer. Indium tin oxide as the bottom contact. Indium tin oxide is transparent and conducting. Okay, that's why it's used as a bottom contact there. And the whole thing sits on a glass slide. To the indium tin contact, you make one wire. To the top here, you make another wire. Attach the sources, and there we go, we've got an LED. So the whole transport layer injects holes into this luminescent layer. You've got the electron transport layer that allows the injection of electrons from the other side, and they combine in the luminescent layer, which in this case is the same as the electron transport layer, though you can have it differently. And light is produced, which in this case is now going to be emitted in this direction through the transparent contact. ITO is transparent, and so is glass. And so below here we will get light. This is the basic idea behind it, LED or display technology based on organics. How colors are produced and all, I don't have time to go into. But we'll stop here because I think that's all I have time for. But this is an area I would challenge you to look at more if you're interested. There's so much on the web also, so take a look and see. And if you're interested, find work in this topic. I think it's going to be the future. So anyway, I hope you enjoyed the course. I enjoyed teaching it, and so I hope you learned something out of it on the broad area of electronic materials. I've tried to expose you to the different kinds, not simply semiconductors. And you can take it from there and specialize in whatever you want. So we'll close with that.